Yeah. I think that's fair. But I mean, technically, you can always be the new age parents that decide to follow your kid. But I think that might be a need sometimes. Yeah. Oh god. No. Okay,
Ready to play a game?
check still. No, I'm just checking your. Is the camera on? I think the camera's on, so basically the stream has started. Yep.
Probably stop talking a little bit. Strange names.
Nah, don't worry. I mean, the mic's all over there, so it doesn't catch.
Is it my mom?
Radio. I think the doors are open, so people are mostly gonna watch it online if they're gonna watch it.
Hello. Yeah. Can you make comments? Is there a live chat?
I don't see.
Ja sam Marija. Drago mi je.
Andrew?
Ćeš pa brzo počnem čistiti. Dobro.
Kako ste, ja nisam shvatila kako se povezalo sa Marijom Cicakom.
Aha, Marija znam već 100 godina. Mi se znamo kao dosta ljudi. Ja sam sam htio studirati, sam odustao zadnji čas i išao na fiziku. Može biti na ti. Ti jesi fizičar kako je završila fakultet?
Ja sam krenula paralelu studirati, a onda sam se spojila na kraju. U paralelu sam prve skoro 2 godine gurala, a onda sam...
Imali smo jedan dečka tako je završio ovo dva.
Da.
Da.
A jedan pa drugi ili...
Istovremeno.
Istovremeno?
Onda, da to ti bilo 84. do 88. I onda je otišao na izvrsni postdoktor u Americi, radio u Berkeley, doktorirao u Berkeley, radio u teorijskom institutu za fiziku sa Almom u Trstu i još kod Marylandu kod jednog Nobelovca. Da bi mu pukao film i otišao na industriju, jer onda programira.
A di je Dobro, ja znam ovdje na koji šta... Ne, ovo je prvo
To je onda 10 godina. Sad to normalno, po starome, otprilike izgleda.
Aha, dobro.
Meni je drago da nisam ni počeo. Sam se rekla, vas je dobro znanje ko sam
Shall we start? Okay. Right, so hopefully there are some people watching us on YouTube. If not, I'm very glad to see at least someone here. So just as general information, I'm the new president of the
let me remind myself. The computer chapter of the IEEE Croatia section. I'm Lucia Petricioli, and I hope I will be able to actually organize more interesting lectures for all of you and whoever might be interested. Right, so I would like to welcome you in the name of the computer chapter and the education chapter of the IEEE Croatia section. And, well, I would like to at least read the bio of our lecturer to know who is going to tell us about this very interesting topic. So, William Andrew Simon received his PhD in electrical engineering from Embedded Systems Laboratory at the Swiss Federal Institute of Technology, Lausanne, Switzerland in 2022. He is currently a postdoctoral researcher at IBM Zurich, in the Cloud Computing and AI Design Department. His current work focuses on in-memory computing-centric architectures for accelerating deep neural networks. So whoever is interested in machine learning should learn a lot. So thank you. You may continue.
Yeah, thank you for that intro. So this was a bit of an impromptu talk. Professor Pelle asked me to give it approximately 3 days ago. So, and I wasn't even sure what the audience was going to look like. And I see now that we are mostly, looks like younger people. So I think we can say this is going to be sort of informal discussion where I present both what I did in my PhD and what I'm working on now at IBM. And if something's unclear, you have questions, feel free to interrupt and raise your hand and just say something. I'm also focusing, I'm not trying to convince you that this is like the next best thing. I'm more interested in like explaining how it works. So I have a few results at the end, but most of it's just going to be trying to slowly go through the actual methodology. My fiance still, after 2 years, doesn't know exactly what I do. So if I get to the end of it and she finally understands how it works, then I'll have considered it a success. So just a little bit of background on kind of the motivation for this in-memory computing. So in the last decade or so, we've seen a huge increase in the number of these so-called like edge devices. So from cell phones to smart refrigerators to smart glasses, whatever. We're seeing more and more of these. And also at the same time, we have more and more complex workloads. So augmented reality, artificial intelligence, 4K video streaming, voice recognition, all of these things are being done, and they're being done on smaller and smaller and lower powered devices. So the question is, how can we increase the compute power of these devices while staying within the small area footprint requirements and energy consumption requirements of these devices? So just a quick crash course on computer architecture. Some of you might know this guy, John von Neumann, one of the greatest mathematicians of the 20th century. He did everything, math, physics, economics, computing. And one of the things that he's most known for in computer science is the concept of the von Neumann architecture. So the von Neumann architecture basically separates structures in the architecture between compute and storing structures. So you have a processor and you have memory. And in between that, you have a bus that does the communication. Now, this has worked very well by kind of binning and isolating these two structures and allowing us to develop both of them separately. However, it leads to this idea of the von Neumann bottleneck. And basically what we've seen is that over the last number of years, as we've developed and improved these components, the processor and the memory have become much, much faster, while the communication connection between them has remained relatively slow comparatively. So that's the bottleneck of most of the traditional architectures these days, is this communication structure. So a lot of research is being done into how we alleviate this von Neumann bottleneck, and in-memory computing is one of these methods of alleviating this bottleneck. And basically the idea is that we want to utilize the memory array to perform computation. And this enables us to perform many operations simultaneously because the memory is very wide. Typically the largest, not to say the largest, but a vector processor in a CPU might be 32 words wide, whereas your memory, when you read it out, you might read out 512 words simultaneously. So we have a much wider data to work with there. And it also reduces the data movement between memory and processor, because if you do the computation at the memory, you don't have to move it through the communication channel to the processor. And this in-memory computing concept represents a wide range of topics. So from hardware, how do we build these in-memory computing devices? It represents architecture. How do these in-memory devices coexist with existing hardware? Or do we develop entirely new architectures that are radically different from the traditional computer architecture? Software. How do we use these IMC devices? How do we redesign algorithms to use these new devices? So that's, my PhD was focusing on the whole range of that, and we'll go over kind of two different methodologies for this. So we have digital IMC and analog IMC. So we'll take a look at both of these methodologies separately, and then kind of compare and contrast and see how their approaches are different. So first, digital in-memory compute. So in my PhD, I worked on a in-memory computing accelerator called a bitline accelerator for devices on the edge, or BLADE. That's what was the acronym. And the idea here is this is a digital in-memory computing architecture for edge devices. So focused for these low-power devices that I mentioned earlier. And again, the idea is that you perform massive single instruction, multiple data operations on hundreds of bytes of data simultaneously. And we support this I developed kind of a hardware software stack that supported it at all levels. So we did circuit designs in my PhD. Then we integrated it into the existing processor and memory architecture. And finally, we developed software support for it at the application level. So applications that could use this bitline accelerator for devices on the edge. So what does it look like? Basically, here's a kind of a standard von Neumann architecture. So you have your processor, you have your memory. Inside your processor, you have compute units. And here, again, we see this bottleneck is we see the connection here is the bottleneck. So the idea is we take some of these compute units and we move them into the memory. So we put them underneath the memory so that we can avoid this communication bottleneck. And what that looks like here, so this is a typical memory subarray. So this is SRAM memory. So this would be your cache. So you have your hard drive, your DRAM, and your SRAM. And your SRAM is typically your smallest memory that's closest to the CPU. So that's what we targeted BLADE to. So you take your cache and you insert bitline logic underneath the cache. And this bitline logic looks something like this. So this is what your standard SRAM memory looks like. So these are bit cells here. These store bits, binary values, zeros or ones. And you read out on the sense amplifiers at the bottom of the wires connecting them, you read out their values. So let's say we have A and B. So A is a value of 1 and B is a value of 0. And bit cells, which is it's a single unit that stores 1 bit, they always come in complementary and inverse values. So you have a 1 on one wire and a 0 on the other wire. Now typically, you would, to read, like let's say we want to read A, you would read A by pre-charging the bit lines. So the 2 blue lines, you charge them. And then okay, so ignore that for now. You activate one word line let's say we want to read A. So we activate one word line. And what that's going to do is this blue, the right bit line will remain at 1 because the value of A is 1, while the left bit line will fall to 0. It will fall to the value of what's in on the inverse bit cell. And then the output here will be 1 and the output here will be 0. And you've read out your value of A. For B, it would be the opposite. The right bit line would drop to 0, the left bit line would remain at 1.
What is bit line?
A bit line, it refers to, so these are bit cells. Each of these are bit cells. The vertical wires are bit lines. So it's a bit line connects many bit cells in a column.
And then you have multiple columns to
yes.
To constitute a word.
Exactly. Yeah. So each of these wires here represent 2 bit lines, and the horizontal lines are word lines, and so you would read multiple bit lines out, and to get 1 word. So maybe 8 of these you would read out to get 1 word out. So the trick that we do to do in-memory computing with this is instead of activating one of these word lines, we activate 2 of them simultaneously. And what this does is, so this left bit line drops to 0 because the A bar is 0. So this line drops to 0. And this has no effect because it's not charging the bit line. It just drops to 0. And this results in a NOR operation between A and B. So it's a bitwise NOR between A and B. Meanwhile, on this side, because B is 0, the right bit line also drops to 0, and this results in an AND between A and B. So if this was 1 and 1, then this line here would stay charged, and we would read out 1. If A was 0 and B was 0, then the left bit line would stay charged, and we read out 1, which is the NOR of A and B. So in this way, we can read out a NOR and an AND simultaneously from any 2-bit cells that share a column. And then if we insert a NOR between the 2 sense amplifiers, we also read out the XOR of this. So we can read out a NOR, an AND, and a XOR for the cost of a single NOR gate that we add to the whole memory subarray. And this is the very kind of bread and butter of digital in-memory computing for SRAM. There's also DRAM in-memory computing. I think there's even flash in-memory computing now, but for SRAM in-memory computing, this is the bread and butter. My PhD involved this part, which was basically how do we extend this, how do we extend these 3 bitwise operations and kind of connect multiple columns to be able to do additions and multiplications. And that was 4 years of research. It was quite a thing. But we developed a couple chips to showcase that, which I'll show at the end. But this is the basic, I think for a very entry-level explanation of digital memory computing, this is what I want you to take away from it. So again, going back to the architecture, what does this look like? So we have, again, we've placed these NOR gates essentially underneath the memory arrays. And what this lets us do is it lets us read out a whole row of bit values, perform an operation, and then immediately store them back into the subarrays. So we avoid this computation here. So this increases our performance because we're avoiding the data movement. It decreases our power consumption because the data movement is expensive, and we also can set this to idle, which we reduce the dynamic power of it. So we're using a whole lot less of the digital fabric. And if we do this correctly, then we can we incur a very small area overhead for this. So in our work, I think to do multiplications, we were looking at something around 8% area overhead. So it's not a huge area overhead to add this.
Can I ask something?
Yeah.
So on the previous slide, if I understand you correctly, you simultaneously access 2 words.
Yes.
And then immediately you can have the result 3 different logical operations.
Yeah.
But you now said that you also immediately store it into a 3rd location. Mm-hmm. How do you do that?
So it's 2 cycles to store. So you read it out and store it into a set of registers, and then on the next cycle you put it back out. And we developed a pipeline so that you could do the read, compute, write in a pipeline fashion. So your latency ends up being 1 cycle in the end. Yeah. Yeah, and I wish I had time to go into how the addition and multiplication works, but as soon as I put the circuit design on the screen, it's just going to be another 30 minutes of explanation. So, yeah. So this is digital. And digital, again, so what's interesting about this is primarily focusing on current setup. So you put this into a von Neumann architecture as an addition to the von Neumann architecture. And this is as opposed to analog. Analog is a radically different approach to this whole in-memory computing paradigm. So we'll look at a bit at that. So this is a 2D mesh of in-memory compute devices, analog compute devices, and this is what we are working on at IBM. So the idea here is that this is actually targeting an entirely different system. So this digital in-memory computing, and over my PhD, we were targeting edge devices, and this is targeting server systems. So this is going for huge server racks. It's competing with NVIDIA. We're trying to beat the A100. So we're really going for the top of the line kind of computation ability here. And also, this is primarily targeted to deep neural nets. So we're really targeting AI as opposed to in my PhD, we looked at cryptography, we looked at video encoding, we looked at a wide range of applications, whereas analog in-memory computing is generally very focused on AI. And this is because with analog in-memory computing, we can perform huge vector matrix multiplications at extremely low power, which can then be chained to perform matrix-matrix multiplications, which is the bread and butter of neural networks. So we go for very, very low power, very large matrix multiplications. And again, this is kind of, we're working to support this at all levels of hardware and software. So IBM does circuit design. We do integration through multiple different types of simulators and emulators. And we're also working on developing pipelines to convert models from PyTorch or from TensorFlow into networks that run on these analog in-memory devices that we've developed. So what does this look like? It looks, again, radically different. So analog in-memory computing. So these are based on what are called non-volatile devices. So this is an example of a non-volatile memory device. So you have a metal electrode on the bottom and an electrode on the top, which is not shown here. And then you have, for us, we use what's called phase change memory. So phase change memory, basically, this is glass. And this glass can have two structures. It can be crystalline or it can be amorphous. When it's crystalline, it has a very low resistance. And when it's amorphous, it has a very high resistance. So what we can do is we can run a current through the glass, and based on the amplitude of the current and how long we run it through the glass, we change the properties of the glass. So it can either be purely crystalline, purely amorphous, or it can be somewhere in between, which causes it to have a variable resistance. And this, we can put these in a huge crossbar array, where again we have columns of wires, rows of wires, and then we can use the classic current and voltage laws to, these can be charged, these can be put into roughly 16 different resistance states that can be, because there's always noise as you're charging it, but roughly 16 different resistance states that can be can be identified as different from each other. And so you put these in this big array, so each of these little resistors represents one of these NVM devices, and then you run, you put inputs into a digital analog converter, which converts it into a current, and you run that along the rows, which is then summed as currents along the column using Kirchhoff's current law, and read back out as analog, from analog to digital. And this gives you basically the addition of all of these resistances here. So if you imagine each of these resistances represents a weight in a neural network, and each of these inputs represents an activation. Then you can do you can multiply all of your activations by like a column of weights, and have the addition of that out in one cycle. So we run this right now. We've done tape outs with 512 by 512 of these and 256 by 256 of these. So that's 256 by 256, something like 64K weights that we're storing. So we can do a 64K matrix times a 256 vector and get the output of that in one cycle. So this is what this looks like. Yeah. So each of these orange tiles here represents one of these 512 by 512 arrays. We also have some digital logic, some memory for storing activations. And then if we take kind of a network here, so like a series of convolutions, you would take, so for example, this convolution is a 1x1 with 1024 channels going to 2048, and you would take those weights and you would map them into a row of these tiles here, and then you could feed all of your inputs in and get the outputs out in one cycle. A key thing about analog in-memory computing is that the weights are stationary. So once you store the weights, you don't change them, like as you're doing inference. So normally with digital, you stream the weights in from your DRAM and you evict them as you don't need them. But here, you store them and they stay there, because writing to this analog memory is very, very energy and time consuming. So we don't have the time to constantly read and write from it, which is why we have tons of tiles. So you have to have enough tiles and enough capacity to store your entire network and not have to be constantly reading and writing it, which is why This is not von Neumann. You know, there's no processor somewhere and memory somewhere. It's just all memory and process, and the compute is mixed into it. So this is why it's a radically different setup. Yeah.
Is it useful for neural networks? For neural networks to be changed like a bit every time. So is it growing here? Or
yeah. So that's the training process is normally done offline. So you do the training on a GPU, you do it wherever, so there's such a thing as online training. That's what my fiance is doing research on, is how you kind of constantly are retraining the network as you're doing it. Here, that's not. We have done research into online training, but we have not pursued it in depth because of this write cost. But we're mostly focused just on inference. Yeah. So yeah. Yeah. So this kind of illustrates the difference between the two architectures. So Blade is put directly into the memory, and this is a very standard memory or a computer, like von Neumann computer architecture. Whereas here, you'll have the host processor, some memory, and then this huge huge array of analog tiles off to the side. And it will work more like an accelerator, where the processor will say, "Hey, do this thing." It does the thing. It says, "I've done the thing. Here's the result," and it gives you the result back. Yeah. So some results that I'll quickly go through. What time it is? Okay. So we looked at so these are from the PhD. So this is focusing on some digital results. So we looked at data movement. So this just kind of illustrates the effect of data movement going on between if you're moving data between memory, how does that impact your results? And basically, what we found is that this graph shows the number of the performance gain. So just compared against just a CPU. And the number of operations performed between moving data from the memory, from off-chip memory, so DRAM, to the memory that has the blade, that has the in-memory computing processor. So if I have some data in DRAM and I want to do some in-memory computation on it, and I move it into the cache that has blade, and then I do the operation. Yeah.
You're constantly talking like cache processor are like.
Yeah.
Since you said that this is designed with deep neural networks in mind, are you talking about the GPU cache and the GPU processor, or the CPU?
Yeah. So this is looking at the CPU processor, and it's taking the CPU processor. So again, Blade is going for low-level devices, edge devices, so low power, low area.
No GPU.
Yeah, no GPU. Yeah.
Ah,
no
yeah.
GPU. So we compare against we use as a benchmark the ARM Neon vector SIMD accelerator. So ARM has their own single instruction multiple data accelerator. They can do, I think, up to 128 operations in parallel, and it's built into their processor. So we compare against that because it's good for doing lots of operations simultaneously. But we're assuming that there will not be a GPU in the system because it'll be your sunglasses or your refrigerator. So here we integrate Blade into the processor cache. And it's here in the L1. It could be here also in L2. But for the sake of my PhD and for just getting the work moving, we just kept it in L1. So basically the x-axis here represents the number of if I take data x and I move it into the L1 cache and I perform an operation on it using Blade, and I perform one operation on it, what benefit do I gain? Because it costs me something to move it from L2 to L1. If I move it here and do 2 operations, or 3, or 4, or 5, the more operations I do on it, the more I negate the effect of the data movement. And what we find is that around 30 operations per moving it from L2 to L1, we gain 3x, about 3.5x performance gain. So that's how much. So basically, we need to do a certain number of operations before it's useful to actually use the in-memory computing architecture. Fortunately, for something like cryptography, you perform over 400 operations per data access, and cryptography is all bitwise operations. You wouldn't even need to do additions or multiplications. You would just need that original NOR gate, and you could get a 3.5x performance gain for cryptography. We also looked at video encoding, and also we looked at neural networks for, oh, actually, I have a slide on that, yeah. So maybe I won't go into the difference between these two, but for neural networks, so this was considering ResNet 18, and we looked also at something like 3x performance gain for neural networks using Blade to accelerate the memory. This drop-off here, we were looking at the effects of the different memory sizes. So the 32 kilobyte cache, once you go up to an image size of 64, you have a huge drop-off in performance because the image no longer fits into your memory. And so now you bring back this communication where you're having to bring in a bit of the image, do operations, then evict that to bring more in. And if you have a larger memory size, of course, you can then fit it again, and so you regain that performance. This is for the analog, a bit of analog results. So the important thing to note here is that these tiles have a very, very good energy efficiency. So we get a 100 teraops per watt. So 100 trillion operations per watt can be done on these analog tiles, these 512 by 512 tiles. However, there's a huge gap between peak and sustained performance. So peak performance, if you are able to use that tile 100% every single cycle, you get 100 tops per watt. But as soon as you start bringing in the application, you have a huge drop-off. So this is different networks, and what we see is for like RNT, your tops per watt, when you start actually running an application on it, and that application has stalls, and there's conflicts to the main memory, and there's conflicts like moving the data between the different tiles, you drop to 60 tops per watt. For CNN, for convolutional neural networks, you drop to, 30 tops per watt, so you have a huge drop-off. And so this kind of hardware-software co-design where you say, this is my hardware architecture, now how do I map the network into those tiles such that my communication is good, I have this minimal stalls happening in between the different layers, is very, very important, and something that's ignored often by many people. Really just focus on getting that tile 1,000 tops per watt. They really push the tile, and they completely ignore the architecture and the higher level application side of things. So that's an important part for both. You have to pay attention to both parts of it. So yeah, in the end though, we just to give a reference, we even with this kind of dropping to 70 and 30 tops per watt, we're between 40 and 140x more energy efficient than an NVIDIA A100 GPU. So we really are very, very energy efficient comparatively to the current A100s. I don't know if it's the current anymore GPU, but it's up there in the last couple of years. So it's a highly energy efficient system. So yeah, these are a couple examples of the works that we produced. So these two chips were produced in my PhD. So these have a Blade on there with 32 kilobytes of SRAM cache with the Blade attached. And this is the Hermes chip, and these are two analog tiles that was produced by IBM in 2020, I believe. So these are it's hilarious, this chip is gigantic, and these are the things that we're testing on it. These are 256 by 256 arrays that we've used extensively for all kinds of different kind of pretty wide-ranging topics like DNNs, but also hyperdimensional computing, if you know it. We are testing that on here. This is basically our big test bed for all of our experiments right now. Yeah, so I think that concludes. So again, in-memory computing, it's a way to alleviate the von Neumann bottleneck by moving. The main point is to move the computation from your processor into your memory. Digital in-memory computing is typically integrated directly into the existing architecture, so we put it into the cache of a processor. And that can be used to accelerate a wide variety of workloads. We looked at cryptography, video encoding, DNNs, whereas analog IMC, it's a radical departure from the traditional architecture, and it's very focused on accelerating deep neural nets. So it's a go for broke for this kind of domain is kind of taking over the world right now. We were were joking the other day that if we can get this analog and memory computing in the toasters, then you'll have chat GPT in like your toaster. It'll just be everywhere. So we're pushing that really hard. So yeah, that's that. Thank you for your attention, and any questions are welcome. Yeah.
I have a question about the slide where you compare the energy efficiencies with like your approach and the A100.
Yeah.
Why did you decide for int8 precision?
So this, so the output of the tiles is in. The output of the tiles depends on your ADC, basically, like how precise your ADC is, and it depends on how precise you can get your PCM devices, like the resistances. And the trade-off between having a good dynamic range in the ADC and having like not a lot of noise is, it's 10 bits actually, so the ADCs put out 10 bits, and then we do some calibration to try to eliminate more noise, and it comes out to 8 bits. So that's basically the kind of the optimal trade-off between bit precision and noise between the, from the coming out of the tile. And the A100 now, they have int8 processors inside the A100, so it makes a good comparison. But we do have the ability, so yeah, so that's a good thing, yeah. So the matrix, vector matrix multiplications are done in int8 precision. We have the digital components can work in float 32 for the activations in between the layers. So, yeah.
So did you look at whether this energy efficiency through time is correlated with how heat is managed inside the tiles or inside the whole system? Mm-hmm. So like if 2 tiles are used really frequently and they have a lot of heat generated, mm-hmm. whether that impacts energy efficiency like in a big way. Mm-hmm. Sort of.
So from what I understand, because I'm at the I'm at the architecture level, so I take what the physicists give me and I try to make a chip out of it that like can be used for applications. But from what I understand, there's not the heat. The heat coming off of the tiles is not very significant. What more impacts these different, like the reduction of tops per watt, is the efficiency of mapping the weights onto the tile. So if you have a fully connected layer and you have 512 by 512 weights, then you have 100% mapping efficiency. You map that entire tile, layer into one tile, one 512 by 512 tile. And then when you use it, you use the whole thing. If either your network is, or your layer is larger than 512 by 512, then you have to map it between 2 tiles, and then you have to communicate between those to add up the partial sums. Or if it's less than 512 by 512, then you map it into a tile, but you don't use the whole tile. There's like some left off, and then you have static power consumption, but it's useless, like it's wasted. So that's where you start to have this drops in energy efficiency. So a lot of, I just want to say, like, architectural optimization is things like mapping 2 layers into one tile, or making sure that if this tile and this tile are part of the same layer, that they're sitting side by side so that the values come out and can be immediately summed up, or working on kind of your mesh connection to do like automatic concatenations between different tiles. If this tile does one half of it and this tile does the other half, that it comes out kind of simultaneously and next to each other. And those are the kinds of things that let you regain that lost energy, that lost tops per watt. Yeah. I don't know if there's a way to get questions off people online. I don't think there's any live chat.
Not sure.
Okay.
How does the future look like? In a sense, how much time you need to get this in the field? I don't have the slightest idea how is it with all these devices.
Yeah.
Is it a 20-year process or a 2-year process?
Yeah. So there's a big push for on the non-volatile memory side of things from a few big companies. that we have contracts with that I can't like say who they are, but the contracts are running in the next, I would say, 5 years. Like that's kind of the length of these collaborations that we have working, and the idea is to get something that works. I don't know, like yeah, I don't know. I can't really say. Basically, I can't really say. I would say we would love to have something in the next, to make it a very conservative number, in the next 10 years. That's like a very conservative timeout. Yeah, but PCM is used. I believe Sony. They have a camera that uses PCM memory in their camera, because so the technology, the non-volatile memory technology, it's already being used. Like it's in devices. It's a very niche product because of the long write times. But if you have to write something and then you write it once and don't touch it again, then it can be very useful. So yeah. Yeah.
Okay, so basically the idea is that if you want to overcome the bottleneck between processor and memory, and you put bits of processor into the memory.
Yeah.
Okay. So there must be some trade-off in or some optimum with regard of the complexity
yes,
that you want to
100%.
achieve. So if computation becomes more and more complex, you basically get again your
you have a processor again.
CPU.
Yeah. Yeah.
Because CPU has registers, which is small parts of it.
Yeah.
Okay.
Yeah.
So can this have use for general computation? For example, can we get faster laptops out of this, or is it for very special problems?
So I think that again, the objective of my PhD is this idea, exact thing. Like, okay, how complex do you go? How far off the beaten path do you go? Like most kind of SRAM-based in-memory computing devices use 8 transistor bit cells, or even 10 or 12 transistor bit cells. So the standard number of transistors in an SRAM bit cell is 6. And when you go to 8, you automatically increase the area by 30%. So they instantly, their array of memory is 30% wide, is larger. And I mean, we had we produced it with IMEC, no, not IMEC, TSMC. We produced this with TSMC, and they said, do not touch the array. Like, do not touch the memory subarray. You cannot touch it. Like, if you do, we're not interested in it. So my objective in the PhD was say, like, if we wanted to make this tomorrow, we could do it. And we did do it. Like, we made it in 4 years. And I think that level of complexity was enough that it could be used for, in the field. It could be used in your laptop or your cell phone or wherever. Whereas if you mess with if you go to 8T or 10T or 12T, you have to justify a lot more performance gain to convince people that it's worth, switching, like, making it that complex. Yeah.
Is there a specific reason why you decided to use PCM instead of like filamentary members or something?
I'm sure there is.
Okay.
I'm not the person to ask. Yeah. They just tell me these are the parameters. This is the noise, roughly the Gaussian noise with that you'll get from it. These are how off your weights will be, and then I work from that. But we've been using PCM for years now, so I think it was a decision made a long time ago.
So like it's like a well-established, stable technology that
I think that's kind of what it is. Yeah. There's some other questions then.
One more question.
Yeah.
How, for most of edge applications that you see, edge devices, how big the whole thing should be? I mean, the capacity, the size of the things.
Yeah.
Because my understanding is that this is now still experimental.
Yeah.
But in order to use it in wide range of devices, a typical size of the thing would be.
Yeah. So what I can say is that we're working on a device now in genomics like genome processing, and we're targeting, we want to have our accelerator to be around 15 to 20 millimeters squared for to go on a device that's about that big. So for that big, we want something 15, 20 millimeters squared, which it's kind of hard to put that in a reference of something else, but it's small, basically. I mean, like, it's really small. You don't have a lot of room to play with.
Okay, but how wide words are?
So
because
that,
you said it's 512, 512. What?
yeah, so 15, 20 millimeters squared would maybe be enough to hold around 4.5 million weights. So, which is tiny. I mean, we were struggling to find use cases for that. So it is very small, and it involves a lot of kind of hardware software co-design. Like, you know, okay, if we're working on something this small, how do we make something, you know, that's like, how do we use it, like, in a way that's actually like innovative or useful. I think Resonant 18 is something like 18 million weights, so, you know, it's like it's quite big. But we found a use case for it. I mean, hopefully there'll be a paper on it in 6 months, and then I can say this is the use case for it. But for now, I can say there are use cases for something that's only 4.5 million weights. It just involves a bit more, you know, innovation, I would say. Yep.
Like, this work is done with edge devices in mind, and like here you are comparing an energy efficiency with an NVIDIA A100.
Yeah. So there's so the digital one was with edge. My PhD, Blade, was edge devices. IBM has mostly focused on server systems, actually. So that's why we're comparing to A100. Now we have a project where we're beginning again to focus on embedded, I'm beginning again to focus on embedded devices, and IBM, for the first time, is looking at embedded devices for this work that I'm working on now. So this is a comparison to A100s because IBM has traditionally been in the server realm of things. But we're trying to, you know, see how can we, because, I mean, if you look at this, that's highly scalable. Like, you can go up and down with that. This can be, if you just take this corner here, then you just have a few tiles. You have CCs are like compute cores, so they're like digital compute for doing, like, you know, ReLU and batch norm and kind of all the bits in between the layers. But yeah, you could just take this thing here, cut it out, put it, you know, on an independent device, and say, all right, now what can I do with this? So that's what we're kind of beginning to look at a little bit now. But traditionally, we've taken this whole thing you can compare against an A100, with the big block.
Yeah, okay. Like, so your PhD was edge devices, and then your IBM work is more like
server level,
not just edge devices.
Yeah.
Okay, nice.
Yeah.
For edge devices, did you take into account the energy consumption when standby, or like since you said?
We consider define standby. I mean, like when everything's idle, or
have a smart speaker that's supposed to do like on device voice processing.
Yeah. No.
And it's not that.
No. So we don't consider that. We don't. I mean, we consider the static power consumption of Blade. So like, if the thing is just sitting there and Blade is sitting there and not doing anything, you know, what's the static power consumption of that? But we start the measurement when we start the application and stop the measurement when we stop the application. So it's only that time frame that's considered. Yeah.
Also, question for the analog. You said that writing is an expensive operation. Is the same for Blade?
Is it the same for Blade?
Yes.
So no, because these are SRAM cells. So it's just your standard cache memory. I mean, like, basically, so in this configuration, any operation you do in Blade, that data movement would have to have been done anyways, because if you didn't do it in Blade, you would do it in the processor. So like, you have to move it to the L1, the level 1, no matter what. So yeah, it's not a cost. I mean, like, if I had another 4 years, we would put Blade here on the L2. But the problem with that is the L2 is typically shared, so then you have coherency, like, you know, you're modifying data which is being shared between multiple processors, and they're all expecting that data to be the same. So then if you make a change, you have to tell the processor, all the processors, I changed it. Whereas in L1, it's private. The level 1 is only one processor, so it's simpler. So yeah. And they do now have, I mean, there's people looking into DRAM, in-memory computing. The farther down the stack you can get, the better, because you're not moving, you know, if you don't have to move the data from the DRAM to the cache at all, then you're saving even more energy on data movement. Anything else? Cool.
Okay. So, well. Okay, thank you very much to all of you who attended, hopefully those online as well. And I hope to see you at the next lecture, whenever that will be. Thank you.
It's half of my. Actually, I mixed quite a bit of my. I usually like just get your public defense, and I'm like, I can't just. That's not honest. I have to talk about new stuff too. So I mixed it.
Poštovanje, ja sam Marija Stipčević, Srđe Boškovića. Mislim da smo se vidjeli u nekim sastancima, ali nikad formalno da. Ja sam radio diplomski na kolekciju. Ali sam jesam.
Yeah. They're safe food remover, live vicariously.
I'm a vicarious.
Yeah, that's.
Thank you for the introduction.
Thank you.
Well, I could give you an easy first person to.
Yeah, I mean.
Get on stage.
Yeah,
I have to figure it out.
Really, thank you very much, because I mean, I know it was last notice. It really
was fun. I enjoyed it.
Yeah, I'm glad.
Believe it or not.
Good.
Ok, vi imate nekog posla sada, pa onda...
Tu sjest?
Jel me sam da radim? Želim počasti s nekim. Ako nije prebučno.
Možete kod mene u sobi.
Može. Sobe su poznane, ja sam Marija. Danas nema sajta, budem strašnik, budem nekog.
Pridružujem se, znam da prekinemo ovaj YouTube stream.
Ok.